Hello everyone, this is Feiyang He. I'm a PhD student from Cranfield University. I'm glad to attend this conference and thank you all for watching this presentation. My presentation topic is the effect of printing parameters on crack growth rate of FDM ABS cantilever beam under thermo-mechanical loads. At first, let me introduce the background of my research. Fused deposition modeling, as one of additive manufacturing technology, has been developed for about 30 years. As shown in this figure, it extrudes the thermoplastic filaments through a nozzle to produce the parts by layer deposition. As for the 3D printing materials, ABS filament is the most commonly used plastic. FDM products can be used in extreme working environment. Fatigue damage due to crack propagation is common under these complex working conditions. The crack resistance and fatigue strength of the product are then significant and critical. Compared with conventional manufactured structures, the printing parameter plays a vital role in the fatigue strength of the FDM structure. This figure shows some printing parameters which may affect the fatigue life of FDM ABS. However, only a handful of studies have evaluated the relationships between these parameters and the crack propagation. One research showed that the fracture resistance increased when the nozzle or bed temperature was increased. Another research proposed that the specimen with 45-degree rust orientation had higher fracture toughness than 0 or 90 degrees. The other test results showed that the dynamic fracture toughness of a vertical printed specimen was higher than a horizontal printed one. After reviewing previous research, we found that only a few parameters have been evaluated for fracture behavior of FDM ABS. Many key printing parameters haven't been considered yet. Furthermore, no crack growth research considered the complex thermomechanical loads of the practical working environment. So our research chose three critical printing parameters, including raster orientation, nozzle size, and layer thickness, and investigated their influence on the crack growth rate of the FDM ABS cantilever beam under dynamic thermomechanical loads. The dynamic bending fatigue test was carried out. The obtained crack growth rate and stress intensity factor were used to develop the empirical crack growth model for the FDM ABS specimen. Let me introduce our experimental scheme. Building orientation, nozzle size, and layer thickness were evaluated as shown in the table. There was a total of 27 different parameter combinations. The test temperature was 50, 60, and 70 Celsius degrees respectively. The geometry of the specimen is shown in the figure. The thickness of the specimen is 3 mm. An initial seeded crack of 0.5 mm in depth was made close to the fixed end of the beam to ensure that the max stress concentration occurred at the exact location for all specimens. The specimens was printed by Ultimaker 2+ printer. As for the experimental setup and procedures, the ABS specimen was fixed on the shaker surrounded by a mica band heater providing the thermal loads. The signal generator and power amplifier provided the sine signal with 2 mm amplitude to the shaker. The specimens vibrated on the fundamental frequency during the test. The accelerometer at the beam tip recorded the acceleration date during crack propagation. The shaker's frequency was changing to keep the beam in resonance all the time. A dyno light digital microscope measured the crack depth during the test. The measured crack depth and the corresponding beam tip acceleration were processed and evaluated later. With the collected experimental data, we calculated the stress intensity factor and the crack growth rate. The stress intensity factor can be calculated by this equation for Model 1 fracture in our test. It is worth noting how to calculate the stress range delta sigma in the research. Unlike conventional fatigue crack growth tests, the stress range was time variable due to varying beam amplitude during the test. An approximate calculation was essential. The average stress range was then calculated. Firstly, we calculated the displacement amplitude at beam tip by its relationship with the acceleration amplitude measured by the accelerometer. Then the cracked beam was assumed as a full cantilever beam for simplifying calculations. The mode shape function for the beam is shown in this equation. We considered the cantilever beam's boundary conditions and calculated the coefficients for the mode shape functions under the fibration with the fundamental frequency. Then we calculated the curvature and bending moment at the crack location. Let's assume the bending moment at the crack tip was constant and equal to the moment on the beam surface. So we obtained the stress at the crack tip by this equation. We calculated the average stress during the test finally. Then, because the crack only propagates when the crack tip is under tensile loads, the actual number of cycles was half, so the mean crack growth rate between two crack depths was calculated by this equation. This figure shows our data process after the experiments. This is the roll acceleration date from the beam printed with X thrust orientation, 0.8 mm nozzle size, and 0.15 mm layer thickness. The initial crack depth is 1.382 mm. We removed the date that didn't vibrate and picked out the peaks and troughs. Then we obtained the displacement amplitude derived from the acceleration at the beam tip and calculated the stress at the crack tip. The number of cycles was also counted. For our findings to date, specimens with different rust orientations printed with the same 0.4 mm nozzle size and 0.05 mm layer thickness were investigated preliminarily. The first-order polynomial curve-fitting method was applied for log data. As a result, this figure shows the crack growth rate change with different stress intensity factors for three rust orientations under 50 Celsius degree environmental temperatures. All specimens show increased crack growth rate with increasing crack tip stress intensity factor. Specimens with the X orientation has the lowest crack growth rate for the same stress intensity factor. The crack growth rate of the XY orientation specimen is between that of the X and the Y orientation specimens. In contrast, the Y orientation specimen has the highest crack growth rate. This means that the X orientation specimen has the best fatigue strength, and the Y orientation specimen has the shortest fatigue life for the same cyclic stress conditions. We also estimated the constants of Paris law for different rust orientation specimens. The experimental results are similar to previous work, as shown in this figure. The initial seeded crack is the lateral on the beam, which is the same as the Y-rest orientation. Therefore, the 3D printing air voids in the Y-orientation specimen has the same direction as the initial seeded crack. The presence of these printing defects between the filaments leads to stress concentration when the beam vibrates. It provides an excellent crack path that leads to quicker crack propagation. Also, the bonds between the fibers are the weakest in air voids areas. The creasing happens earlier in the area with the voids. Furthermore, the bending stress is longitudinal and acts vertically on the Y-orientation voids during the beam's vibration. It also accelerates the crack growth and decreasing fatigue life in the Y-orientation specimen. As for the conclusion, our research evaluated the printing parameters' effect on dynamic crack growth for FDM ABS under thermo-mechanical loads. The preliminary findings of our study are the specimen in X orientation has the lowest crack growth rate. The following study will evaluate the potential impact of different printing parameters on fracture behavior. We will also estimate the coefficients of the Paris law for different printing parameter combinations under different temperatures. The study results will determine the optimal combination of printing parameters and guide future 3D printing setups. Thanks for listening. Any questions?